lab, another applied. I think the only part that's kind of weird about it is trig function. Okay, so we go back to pre-cal. It says a small frictionless cart attached to the wall by spring is pulled 10 centimeters from its rest position. And when I read this, I think, this would be something I would do. I would invent this, pull this and it just goes back and forth, and I just stare at it. Maybe you do it for your cats. I don't know. All right. And it's released at time t equals 0, and it rolls back and forth for 4 seconds. Its position, so right there I know that's my position function. I know this is applied optimization, so probably right now I would just start taking derivatives, because I know I'm going to have to eventually. So I want to know what the cart's maximum speed is. How do you find speed?
The absolute value.
Velocity. So I find velocity. Oh, let me write my function back up here. 10 cosine of pi t. And then I absolute value velocity to find speed. And so tell me what that derivative is.
Negative cosine. Negative sine. Yeah, negative sine, yeah. By t times pi.
Thank you. Now you saw I left that little space there. Yeah. So once again, the derivative of cosine is minus sine. And then by the chain rule, we had to take the derivative of the inside. And again, pi is just a constant, so that'd be like 3t. So we're bringing the 3 out. And so again, I'm going to absolute value this. Well, by absolute valuing it, I could simply bring the 10 pi out, positive, and just be sure I absolute value that piece. Okay? So if I want to know the maximum of, well, let's do it in pieces. What's the max of a sine function? Think of the graph. The 1, yeah. And we could say negative 1 because we're doing absolute value. So if I multiply it by that, then that's my max. And some of you guys remember, what was that called in pre-cal? Okay, nobody remembers. Starts with an A. I put an A for a hint. Amplitude, yes. I'm like, some of you remember it. Okay, nobody remembers it. All right, and so that's the first part. Is the cart moving that fast? Well, all I did was I graphed, you're going to see here, I didn't care about the amplitude because all the amplitude is doing is stretching it, right? I mean, you could do that. If that makes you feel good about yourself, we'll put 10 pi's up there. And so what I'm looking at is when is the cart moving that fast, the maximums, so I could just simply look here, but remember I'm doing absolute value, so those count as well. And so I'm going to say, I don't know if you can read this because I can barely read it. That's a half, so 0.5, 1.5, 2.5, and 3.5. So in other words, that's my time. So when is the cart moving that fast? I'm looking at my max and mins. All right, and I stopped here because remember they said they give me that restriction 4 seconds. All right, when is the cart, oh, the same thing. All right, where is the cart moving the fastest, and what is the magnitude of the acceleration then? Well, again, the only word that really pops out to me is acceleration, because I know acceleration means to take another derivative. So let's go back to my original function, and then that was supposed to be a t. And then we took the derivative of it and got minus 10 pi sine pi t. So I know acceleration. I'm going to take the derivative again, which would be what?
Negative 10 pi squared.
Very good. Excellent. So, and again, my magnitude, I'm going to absolute value that. So I'm going to end up with this 10 pi squared and then cosine pi t. And I look at times that acceleration equals 0. Well, remember, this is a number. That's not a variable. So I need to know when would that equal 0 and it's got to be at something of a t value that's going to make the cosine 0. So kind of sort of remember things like pi over 2, 3 pi over 2, things like that, kind of sort of? No? The unit circle?
What's that?
No. The thing I didn't make you guys memorize either. I mean, why do you memorize a unit circle? That's really, you know. Let's just have a test on the unit circle. Okay. So again, when it's moving fastest, the acceleration. And I'm going to do show you the graph. I've mentioned this before in here, and it's just kind of, we don't do as much as BioCal does. BioCal finds this acceleration, and so in other words, at these particular times is what I'm looking at. So, go away. So this would be where my time equals 0, 1, 2, 3, 4. In other words, because I'm substituting this into my position function. And so if I look at these times, let's just look at 1, and let's look at 2. What are those points? Yeah, exactly. And so we don't really, I mean, we find inflection points. Go find an inflection point. What's an inflection point? Where the second derivative equals 0, and that's what I just said, where acceleration equals 0. We just don't really do it a lot in words, because again, you're in a theoretical class. But that's actually, and you can see that's where my slopes are going to be the steepest there, okay? And so it's kind of nice to know that that's really what an inflection point is where my acceleration equals 0. And a lot of that, to me, kind of makes sense, because we say, well, that's where it's changing from concave down to concave up, and so on. So that's where concavity is changing. I'll remember to tell you that in a second. That reminded me of something on the test. The cart's speed then, or the magnitude at that time. So remember again, I said the times were, and you saw this on the, I guess we could write all of them down to 4 seconds. And so then the magnitude of cart's position would just simply be the magnitude of my position function, which is going to be my 10 centimeters from rest. What I was thinking of is